On July 1st, 2025, astronomers discovered something racing toward us at 130,000 miles per hour. It's called 3I divided by Atlas, and right now, as you're watching this, it's already passed through our solar system. But here's what nobody's talking about. During its closest approach to the sun, it completely vanished from our view for over a month. And when it came back, something had changed. This isn't just another space rock passing through. 3I divided by Atlas is the third confirmed visitor from beyond our solar system, and it's showing behaviors that have scientists genuinely concerned. Most news outlets are telling you it's harmless, just a comet doing comet things. But when you look at the actual research, when you dig into what astronomers are quietly discussing in their papers, you start to realize there's a much darker story here. And by the end of this video, you're going to understand why some researchers are asking questions that sound like they came straight out of a science fiction movie. Let me start by telling you something that will put everything else into perspective. 3I divided by Atlas is old. Not just old by human standards, not even old by Earth standards. This object formed somewhere between 9 and 13 billion years ago. To put that in context, our entire solar system, the Sun, Earth, Mars, Jupiter, everything we've ever known is only 4.6 billion years old. That means 3I divided by Atlas existed for potentially 8 billion years before our sun even ignited. Think about that for a second. The stars that created this object, the planetary system it came from, the neighborhood of space where it formed, all of that is gone now. Those stars died billions of years ago. The matter that makes up 3I divided by Atlas is literally a messenger from a universe that doesn't exist anymore. But here's where it gets interesting. This thing didn't form in just any old stellar neighborhood. Based on its trajectory and chemical composition, astronomers have traced 3I divided by Atlas back to something called the galactic thick disk. This is a population of stars that formed during a specific period in our galaxy's history called cosmic noon. Now, cosmic noon happened between 9 and 13 billion years ago, and during that time, the Milky Way looked nothing like it does today. There were no spiral arms. The galaxy was smaller, denser, packed with way more gas. Star formation was going absolutely crazy. Nothing like the relatively calm galaxy we see now. The thick disk stars have something really unusual about them. They have much lower metallicity than our Sunday. What that means is they formed in environments that were seriously depleted in heavy elements. Less carbon, less metals, different chemistry entirely. And that ancient alien chemistry, it's baked into 3I divided by Atlas itself. When scientists analyzed the gases coming off this comet, they found something that doesn't match anything in our solar system. Most comets we've studied are water-rich with a decent amount of carbon monoxide mixed in. Pretty standard stuff. But 3I divided by ATLAS, it has a carbon dioxide to water ratio of 8:1. That's wildly high. And its cyanogen production, that's a carbon-nitrogen compound, is remarkably low. This carbon chain depletion tells us that 3I divided by Atlas formed under conditions that were fundamentally different from what created the comets we're used to. It's not just from another solar system, it's from another era of galactic history. So we've got this ancient visitor carrying chemistry from the early universe screaming through our solar system faster than anything we've ever tracked. That alone would make it interesting. But then NASA's Neil Gehrels Swift Observatory detected something that made absolutely no sense. 3I divided by Atlas was bleeding water. Not a little bit, a lot. About 40 kilograms per second. Imagine a fire hose running at full blast, 24/7. That's how much water this thing was losing. Now, comets lose water all the time when they get close to the Sunday. The heat causes the ice to sublimate, to go straight from solid to gas without melting. This is normal. This is expected. Except 3I divided by Atlas was doing this when it was 2.9 astronomical units from the Sunday. Let me explain why that's a problem. 1 astronomical unit is the distance from Earth to the Sunday. So 2.9 AU means this comet was nearly 3 times farther from the Sun than Earth is. At that distance, solar heating should be way too weak to cause this kind of water loss. The ice should be frozen solid, but it wasn't. Scientists calculated that at least 8% of 3I divided by Atlas's surface had to be actively releasing vapor. For comparison, typical solar system comets show about 3 to 5% activity even when they're much closer to the Sunday. So, what was happening? The thick disk stars have something really unusual about them. They have much lower metallicity than our Sunday. What that means is they formed in environments that were seriously depleted in heavy elements. Less carbon, less metals, different chemistry entirely. And that ancient alien chemistry? It's baked into 3I divided by Atlas itself. When scientists analyzed the gases coming off this comet, they found something that doesn't match anything in our solar system. Most comets we've studied are water-rich with a decent amount of carbon monoxide mixed in. Pretty standard stuff. But 3I divided by Atlas? It has a carbon dioxide to water ratio of 8:1. That's wildly high. And its cyanogen production, that's a carbon-nitrogen compound, is remarkably low. This carbon chain depletion tells us that 3I divided by Atlas formed under conditions that were fundamentally different from what created the comets we're used to. It's not just from another solar system, it's from another era of galactic history. So we've got this ancient visitor carrying chemistry from the early universe, screaming through our solar system faster than anything we've ever tracked. That alone would make it interesting. But then NASA's Neil Gehrels Swift Observatory detected something that made absolutely no sense. 3I divided by Atlas was bleeding water. Not a little bit. A lot. About 40 kilograms per second. Imagine a fire hose running at full blast, 24/7. That's how much water this thing was losing. Now, comets lose water all the time when they get close to the Sunday. The heat causes the ice to sublimate, to go straight from solid to gas without melting. This is normal. This is expected. Except 3I divided by Atlas was doing this when it was 2.9 astronomical units from the Sunday. Let me explain why that's a problem. 1 astronomical unit is the distance from Earth to the Sunday. So 2.9 AU means this comet was nearly 3 times farther from the Sun than Earth is. At that distance, solar heating should be way too weak to cause this kind of water loss. The ice should be frozen solid, but it wasn't. Scientists calculated that at least 8% of 3I divided by Atlas' surface had to be actively releasing vapor. For comparison, typical solar system comets show about 3 to 5% activity even when they're much closer to the Sunday. So what was happening? The best explanation researchers could come up with involves something called extended source water production. Basically, there are these tiny ice grains floating around in the comet's coma. That's the fuzzy cloud of gas and dust that surrounds the nucleus. These grains are so small that even weak sunlight at that distance can cause them to vaporize. Once exposed to the sun, these little chunks of ice turn straight into gas and release water vapor, even though the main body of the comet is still way too cold for that to happen. This extended source mechanism has only been observed in a handful of really distant comets, and it tells us something important about 3I divided by Atlas's internal structure. This isn't a solid chunk of ice and rock. It's got this complex layered structure with different compositions at different depths. It's like 3I divided by Atlas is a time capsule with multiple layers, each one preserving information about different stages of planetary formation from billions of years ago. But the water thing? That was just the beginning. In September 2025, astronomers made a discovery that genuinely shocked them. They were studying how 3I divided by Atlas scattered light, a technique called polarimetry. Different materials scatter light in different ways, so by measuring this, you can figure out what something is made of. When they analyzed the data from 3I divided by Atlas, they found a polarimetric signature that has never been seen before. Never. In over a century of astronomical observations, the object exhibits what scientists called an exceptionally deep and narrow negative polarization branch, with parameters that don't match any known solar system comet or asteroid. It doesn't match anything in our catalogs. One of the researchers literally said that 3I divided by Atlas scatters light in a way that places it in a distinct class of small planetary bodies that we know next to nothing about. The closest matches they could find were certain rare F-type asteroids, but even those don't really fit. The depth of 3I divided by Atlas's negative polarization branch is almost twice as large as any comet nucleus we've ever studied. At very small phase angles, that's the angle between the sun, the object, and the observer. 3I divided by Atlas's behavior most closely resembles certain trans-Neptunian objects. These are ancient primitive bodies from the outer reaches of our solar system. Stuff like Huya, Ixion, and Varuna. But here's the thing. Those objects formed in our solar system. They're made of material that condensed from our sun's protoplanetary disk. 3I divided by Atlas formed somewhere else entirely, under completely different conditions. So why would it scatter light the same way? Nobody knows. What this tells us is that 3I divided by Atlas has surface properties or dust grain structures that are fundamentally unlike anything we've cataloged. And the polarimetry revealed no spatial variations across its coma, meaning the dust is distributed really uniformly, which somehow makes the whole thing even more mysterious. Now, at this point in the story, 3I divided by Atlas was already weird enough to keep scientists busy for years. Ancient chemistry, impossible water production, light scattering behavior that doesn't match anything known. But then, in late August and early September 2025, something happened that nobody predicted. 3I Gedeeld or Atlas started getting brighter. A lot brighter. When the comet was first discovered in July, astronomers calculated its expected brightness as it approached the sunday based on the orbit, the size estimates, and typical cometary behavior. They predicted it would reach magnitude 20.5. That's pretty faint. You'd need a decent telescope to see it, but that's not what happened. Instead, 3I divided by Atlas surged to magnitude 19.28. That corresponds to a flux increase by a factor of 5, not the expected 1.5, 5 times brighter than it should have been. Multiple independent telescopes confirmed this wasn't a measurement error or a fluke. 3I divided by Atlas had become far more active than any model predicted. And then it started changing colors. Initially, when astronomers first observed it, 3I divided by Atlas had a reddish hue. This is pretty normal for comets. Dust in the coma tends to scatter red light preferentially. But by September 7th, 2025, astrophotographers who were tracking the comet during the total lunar eclipse noticed something strange. 3I divided by Atlas wasn't red anymore. It was glowing bright green. Now, comets can appear green. This happens when they're producing a lot of diatomic carbon, C2 molecules, which emit green light when excited by sunlight. It's not super common, but it happens. What made this different was what else was happening at the same time. Spectroscopic analysis showed that 3I divided by Atlas was producing cyanide, CN molecules, at an explosive rate. And it was also producing nickel, not iron, just nickel. That's completely unprecedented. In every other comet we've studied, when you see metal emissions, you see both iron and nickel together. They come as a package deal because that's how they exist in the comet's nucleus. But 3I divided by Atlas was producing significant amounts of nickel with absolutely no trace of iron. And both the cyanide and nickel production were increasing at a remarkable rate. Scientists measured that the production was proportional to approximately the 9th power of decreasing heliocentric distance. Let me explain what that means in simpler terms. As 3I divided by Atlas moved closer to the Sun, its emissions didn't just increase linearly. They didn't even increase exponentially in the normal sense. The rate of increase was following a power law with an exponent of 9. That means if the comet moved just 10% closer to the Sun, its cyanide and nickel emissions would increase by a factor of about 2.4. Move it another 10% closer, and they'd increase by another factor of 2.4. This is an insanely steep relationship, and nobody has a clear natural explanation for why this would happen. Normal cometary outgassing follows much gentler relationships with solar distance. This 9th power behavior suggests something else is going on inside 3I divided by Atlas, some internal process that's fundamentally different from typical cometary activity. So now we've got an ancient interstellar object that's bleeding water where it shouldn't, scattering light in ways nothing else does, brightening unexpectedly, changing colors dramatically, and producing chemicals in ratios that don't make sense. At this point, you might be thinking, okay, this is really weird, but it's still just a comet, right? Just a natural object doing strange natural things. And that's what most scientists thought too, until someone looked at its trajectory. Here's something that most news coverage completely glossed over. 3I divided by Atlas's path through our solar system is tilted only 5 degrees from the ecliptic plane. The ecliptic plane is basically the flat disk where all the planets orbit. Earth, Mars, Venus, Jupiter, we all orbit the Sun in roughly the same plane. It's like a cosmic DVD, and we're all moving around in that flat disk. For something coming from interstellar space, from a random direction in the galaxy, to arrive with an orbit that's almost perfectly aligned with our planetary plane, that's statistically really unusual. The random probability of this alignment is approximately 0.2%. That's 1 in 500. But it gets weirder. 3I divided by Atlas made surprisingly close passes to 3 major planets. On October 3rd, 2025, it passed within 0.19 AU of Mars. That's about 28 million kilometers. In cosmic terms, that's really close. On November 3rd, it passed 0.65 AU from Venus. And on March 16th, 2026, it's going to pass within 0.36 AU of Jupiter. The combined probability of an interstellar object making close approaches to Venus, Mars, and Jupiter like this? Less than 0.005%. That's approximately 1 inch 20,000. Now, here's where we need to talk about what this trajectory would mean if, and I want to be really clear, this is a hypothetical. If someone or something wanted to design an optimal path through our solar system. From an astrodynamics perspective, an approach along the ecliptic plane minimizes the delta V, the change in velocity, required for any kind of orbital maneuvers. It's the most energy-efficient way to move around the inner solar system. And those close planetary approaches? Each one provides an opportunity for gravitational assists. You could use Mars's gravity to adjust your course slightly. Venus could give you another nudge. And Jupiter, massive Jupiter, could provide a huge gravitational boost or break depending on how you approached it. If you were designing a mission to explore our solar system, or to study multiple planets, or to achieve gravitational capture into a bound orbit around the sun, this is pretty much exactly the trajectory you'd choose. Now, the scientists who analyzed this were very careful to say this doesn't mean anything is actually designed or artificial. Random chance can produce unlikely alignments. With enough interstellar objects passing through, eventually one of them will have a weird trajectory just by luck. But the coincidence is striking enough that it got people's attention. And then there's the thing that happened at Perihelion, the thing that nobody on Earth could observe. On October 29th, 2025, 3, I divided by Atlas, reached Perihelion, its closest point to the Sunday. It came within 1.36 AU, just inside Mars's orbit. But here's the critical detail that most coverage missed. During this period, 3 I divided by ATLAS passed directly behind the Sun as seen from Earth. It reached solar conjunction on October 21st, 8 days before perihelion. From Earth's perspective, the comet completely vanished behind our star. Its solar elongation dropped below 30 degrees for over a month. At perihelion itself, the separation was just 12.8 degrees. What that means in practical terms is that ground-based telescopes couldn't see it at all. The glare from the sun made observation essentially impossible. For over a month, during the most critical part of its journey through our solar system, 3 I divided by Atlas was hidden from view. Now, this is where things get really interesting and uncomfortable. In aerospace engineering, there's a concept called a solar oberth maneuver. It's a technique where a spacecraft makes a high-thrust burn at perihelion, the closest point to the sun, to maximize the efficiency of that burn. Because of the way orbital mechanics work, a velocity change made when you're moving really fast has a much bigger effect on your final orbit than the same velocity change made when you're moving slowly. It's called the Oberth effect. If you wanted to slow down an interstellar object enough to become gravitationally trapped in our solar system, perihelion would be the optimal place to do it. You'd execute what's called a reverse Oberth maneuver, a braking burn that would rob the object of enough speed to drop its orbit from hyperbolic to elliptical. And if you wanted to do this without being observed, you'd do it when the object was behind the Sunday. This period of solar conjunction creates what some researchers have called a clandestine window, a moment when the object is unobservable from Earth, hidden by the glare of the sun, during the exact time when any theoretical propulsive maneuvers would be most effective. Now, 3 I divided by Atlas is currently on a hyperbolic trajectory with an orbital eccentricity of 6.137. That's extremely hyperbolic. It means the comet should definitely escape the solar system, no question, unless something changed its velocity at perihelion. Calculations show that conducting a reverse Oberth maneuver at perihelion would require a delta V of approximately 5.9 times 10 to the negative 5th AU per day squared, normalized at 1 AU from the Sunday. That's actually not a huge amount of acceleration. It would be enough to alter the trajectory from hyperbolic to elliptical, to trap the object in a bound solar orbit. And here's the thing, that level of acceleration would be really hard to detect from Earth, especially during solar conjunction when we couldn't observe the object directly. Now, before anyone freaks out, let me be clear about something. there's no evidence that this actually happened. The trajectory calculations we have suggest 3I divided by Atlas is still on its original hyperbolic path. It should leave the solar system as expected. But the point is, we wouldn't necessarily know if something changed during that month when we couldn't see it. We're relying on trajectory projections based on observations made before and after conjunction. If there was a small but significant velocity change during the blackout period, we might not detect it until much later. And this raises an uncomfortable question. How many other interstellar objects have passed through our solar system in the past when we weren't watching? How many of them might have executed similar maneuvers during similar blackout periods? Because here's something most people don't know. Interstellar objects can be captured by our solar system through natural gravitational processes. It doesn't require any artificial intervention. A study from 2025 found that approximately 10 interstellar objects may currently be bound to our solar system right now, captured primarily through gravitational interactions with Jupiter. The capture cross-section for Jupiter is roughly 10,000 times greater than Earth's because of Jupiter's enormous mass. Objects captured this way tend to have high eccentricities, really elongated orbits, and semi-major axes larger than Jupiter's orbit. Their inclinations tend to be modestly biased toward prograde motion, meaning they orbit in the same direction as the planets. But there's another capture mechanism that's even more interesting. Under the gravitational perturbation of the galaxy itself, there's a region in phase space where permanent capture can occur naturally. In this scenario, an interstellar object could cycle around the sun indefinitely without ever being ejected back into interstellar space. And without colliding with the sunday, it would asymptotically approach a stable captured orbit just from galactic gravitational effects. So the idea of interstellar objects becoming trapped in our solar system isn't crazy. It's actually expected to happen naturally over long timescales. The question is whether 3I divided by Atlas could be one of them. And that brings us to a paper that caused a lot of controversy. In a mathematically rigorous but admittedly speculative paper, Harvard astronomer Avi Loeb and his colleagues explored a thought experiment. They asked, what if 3I divided by Atlas isn't natural? What would the evidence look like? The paper invokes something called the dark forest hypothesis. This is a solution to the Fermi paradox that comes from Chinese science fiction author Liu Cixin's novel, The Dark Forest. The idea goes like this. The universe is like a dark forest at night. Every civilization is a hunter moving through the forest, trying to be silent and unseen. Why? Because if you make noise, if you reveal your location, you risk being detected by other hunters who might see you as a threat. In this framework, alien civilizations stay silent not because they're rare, but because any civilization that broadcasts its presence might be destroyed by more advanced civilizations that view any potential competitor as an existential threat. It's a pretty dark idea, but it's also a logically consistent solution to why we haven't detected any obvious signs of alien life despite the size and age of the universe. The dark forest hypothesis suggests that advanced civilizations would develop stealth technology and avoid unnecessary contact with unknown civilizations. They treat every encounter with extreme caution because the cost of being wrong, the cost of assuming another civilization is peaceful when it's not, could be total annihilation. Now, Loeb and his colleagues applied this framework to 3I divided by Atlas as a thought experiment. They noted several features that would theoretically benefit an extraterrestrial intelligence trying to study or access our solar system. First, the flat retrograde trajectory allows easy access to multiple planets with minimal course corrections. You could visit Mars, then Venus, then potentially Earth, then use Jupiter for a gravitational assist, all without needing massive amounts of fuel. Second, the perihelion eclipse by the Sun provides cover for unobservable maneuvers. If you wanted to change your trajectory without being detected, solar conjunction would be the perfect time to do it. Third, the close approaches to Mars, Venus, and Jupiter would enable both reconnaissance and gravitational assists. You could study those worlds up close and use their gravity to adjust your path. If 3I divided by Atlas were executing a reverse Oberth maneuver at its hidden perihelion and intended to intercept Earth, Loeb's calculations suggested optimal arrival would occur in late November or early December 2025. That's right around the time when the comet re-emerged from behind the Sun and became visible again. Now, Loeb and his team emphasized repeatedly that this was largely a pedagogical exercise, a mathematical exploration of what would be possible if the object were artificial. They weren't claiming 3I divided by Atlas actually is artificial. They were showing what we'd need to look for to tell the difference. But the paper did note that detecting a non-gravitational acceleration during the perihelion passage would be highly significant. It would be anomalous. It would require explanation, and because we couldn't observe the comet during that critical period, we can't definitively rule it out based on direct observation. Of course, there's another side to this. The side that says 3I divided by Atlas is definitely, absolutely, 100% a natural comet, and all this speculation is kind of ridiculous. And honestly, that side has pretty strong arguments. First and most obvious, 3I divided by Atlas exhibits clear cometary features. It has a diffuse coma extending up to 15 miles across. It has a growing antisolar dust tail that reached 100,000 kilometers by September 2025. It has sun-facing plumes that are characteristic of volatile sublimation. These are things comets do. Natural comets, made of ice and rock. Second, multiple observations show no evidence of non-gravitational acceleration beyond what would be expected from normal outgassing. The Hubble Space Telescope tracked the comet's light curve over multiple days. Everything looked consistent with a rotating irregular nucleus with natural activity. Third, the unusual chemical composition, while strange, is actually consistent with formation in a low metallicity, carbon-poor environment around an ancient thick disk star. It's exactly what you'd expect from cosmic noon-era planetesimals. It's weird compared to our solar system's comets, but it's not weird in the context of where 3I divided by Atlas came from. Different stellar environment, different chemistry, makes perfect sense. Fourth, Hubble observations constrain the nucleus size to somewhere between 320 meters and 5.6 kilometers in diameter. That's consistent with a cometary nucleus. The extensive coma and water production rate match what you'd expect from a comet of that size losing ice. If this were a spacecraft, you'd expect a much more compact, reflective object without all the outgassing and dust production. You definitely wouldn't expect it to be bleeding water at 40 kilograms per second. So the natural explanation fits most of the evidence pretty well. Yes, 3I divided by Atlas is weird. Yes, it's doing things we haven't seen before. But weird doesn't mean artificial. It means we're observing something from a completely different formation environment, carrying chemistry from a different era of galactic history. The universe is big and old and full of weird stuff. Sometimes weird stuff is just weird. But here's the thing that actually concerns scientists. And this is what makes the "it gets worse" part of this story. The genuinely worrying aspect of 3I divided by Atlas has nothing to do with aliens. It's what this object reveals about our vulnerability to fast-moving interstellar visitors. Unlike near-Earth asteroids that orbit the Sun and can be tracked years in advance, interstellar objects arrive with almost no warning. 3I divided by Atlas was only discovered when it was already 4.5 AU from the Sunday. That gave us exactly 3 to 4 months of advance notice before perihelion. If a similar object were on a collision course with Earth, we would have virtually no time to mount a deflection mission. Think about that. Our entire planetary defense strategy is built around tracking objects that orbit the Sunday. We can see them coming years in advance. We can plan missions. We can test deflection techniques. But interstellar objects don't orbit the Sunday. They come from outside, from random directions, at extremely high velocities. 3I divided by Atlas's velocity at perihelion was about 68 kilometers per second. That's more than double the speed of typical near-Earth asteroids. At those speeds, our current deflection strategies, kinetic impactors, nuclear detonations, would be far less effective. The kinetic energy you need to impart to change an object's trajectory scales with its velocity. A faster object requires more energy to deflect, and we simply don't have systems designed to intercept something moving that fast. Moreover, 3I divided by Atlas's hyperbolic trajectory and high inclination make interception extraordinarily difficult. A study found that even the ESA's Comet interceptor spacecraft, which is specifically designed for fast intercepts of long-period comets, would require an unrealistic delta-V far exceeding its capabilities to reach 3I geteilt durch Atlas. A rendezvous mission launching from Earth would need approximately 24 kilometers per second of delta-V. That's beyond the capacity of current rockets without multiple gravitational assists and years of flight time. So, if an interstellar object were discovered on a collision course with Earth, giving us only a few months' warning, we would have no way to stop it. None. We'd be able to track it. We'd be able to predict exactly when and where it would hit. We'd be able to calculate the devastation, but we couldn't prevent it. And here's the even more unsettling part. The discovery that interstellar objects like 3I divided by Atlas originate from ancient stellar populations means they could carry radically different chemical compositions than anything in our solar system. What if an interstellar comet deposits exotic organic compounds in Earth's atmosphere as it passes by? What if it carries extremophile microorganisms that can survive the harsh conditions of interstellar space? What if it introduces completely novel chemistry that we've never encountered? We have no protocols for assessing these risks. We have no strategies for mitigation. We barely have the ability to detect these objects before they're already here. 3I divided by Atlas gave us a wake-up call. It showed us that our solar system is permeable, that visitors from the ancient galaxy can arrive with minimal warning, carrying chemistry and potentially biology from stellar environments we can barely imagine. And there's nothing we can do about it except watch. Now, here's what actually happened after perihelion. After 3I divided by Atlas emerged from behind the Sun in mid-October 2025, ESA's Mars Express and ExoMars Trace Gas Orbiter captured the closest views yet during its Mars flyby. The spacecraft revealed a bright coma, but notably no visible tail at that distance. This was actually kind of surprising. The tail should have been more prominent at that point. But observations confirmed it was still very much a comet, still outgassing, still active. In November 2025, ESA's JUICE spacecraft, which is currently en route to Jupiter, conducted observations of 3I divided by Atlas at its most active post-perihelion phase. But because of the distance and communication delays, that data won't arrive until February 2026. By early December 2025, 3I divided by Atlas became visible again from Earth-based telescopes as it receded from the Sunday. Amateur astronomers around the world tracked it, watching as it slowly faded and its activity decreased. The comet passed closest to Earth on December 19th, 2025, at a safe distance of 1.8 AU, about 270 million kilometers away. No danger, just a distant point of light in the sky. It will continue outward through early 2026, making its Jupiter flyby in March. That will be another opportunity for observation. Jupiter's massive gravity might actually cause some tidal stress on the comet, potentially triggering more outgassing or even fragmentation. And then, after Jupiter, 3I divided by Atlas will exit the solar system forever. Its trajectory will carry it back into interstellar space, back into the dark between the stars, where it will travel alone for millions or billions of years until it encounters another stellar system. If it encounters another stellar system, space is mostly empty. The distances between stars are so vast that even traveling at 130,000 miles per hour, 3I divided by Atlas, might wander the galaxy for the entire remaining lifetime of the universe without coming close to another star. But despite months of intensive study, despite observations from dozens of telescopes and multiple spacecraft, fundamental mysteries remain. Why does 3I divided by Atlas produce water so far from the Sun through that extended ice grain mechanism? What causes its unique negative polarization signature that doesn't match any known object in our catalogs? Why did its brightness surge unpredictably by a factor of 5? What explains the exponential 9th power increase in cyanide and nickel emissions? And perhaps most intriguingly, if gravitational capture mechanisms can trap interstellar objects in bound solar orbits, how many ancient visitors are already circling our Sun, undetected? The sparse population of objects with certain orbital characteristics, high eccentricity, large semi-major axes, specific inclinations, could contain numerous captured interstellar bodies that we've mistakenly classified as native solar system objects. A 2025 study identified 18 candidate objects in the current solar system population that may be bound interstellar objects captured by Jupiter, plus 7 additional candidates captured through other mechanisms. These ancient immigrants could provide windows into planetary formation around stars that died billions of years before our Sun was born. They could be messengers from stellar neighborhoods that no longer exist, carrying samples of chemistry from the early universe. And we might be surrounded by them without even knowing it. So where does this leave us? 3I divided by Atlas will not stay in the Sun's orbit. Its trajectory remains firmly hyperbolic. The mathematics are clear. The observations are consistent. Unless something dramatic happened during solar conjunction that we didn't detect, this comet is leaving and never coming back. There's no evidence supporting artificial origins, no evidence of hostile intent. The comet poses zero threat to Earth. But the worst part isn't about this particular visitor. It's about what 3I divided by Atlas represents. It's the revelation that our solar system is permeable to high-speed objects from the ancient galaxy. Objects carrying exotic chemistry forged in stellar environments we can barely imagine. Objects that could arrive with minimal warning and that we'd have no ability to deflect if they were on a collision course. It's the unsettling realization that we discovered this messenger from cosmic noon purely by chance. If it had passed through just a few months earlier or later, if it had taken a slightly different path, we might never have known it was here. And it's the understanding that right now, today, there could be other interstellar visitors in our solar system that we haven't detected. Objects captured into bound orbits years or decades or centuries ago. Ancient wanderers from dead stars, circling our sun in the darkness, waiting to be found. 3i divided by Atlas showed us that space isn't empty. It's full of travelers, messengers, artifacts from cosmic history. And sometimes those messengers come from places and times so alien to our experience that we struggle to even understand what we're looking at. This 9 to 13 billion year old wanderer, bleeding water in the void, scattering light in impossible ways, temporarily transforming from crimson to emerald green, represents our first real glimpse into planetesimal formation processes during the Milky Way's youth, during a time when the universe itself was barely a third of its current age. It came from the thick disk, from cosmic noon, from an era when galaxies were still young and violent and strange. It formed around stars whose names we'll never know, in a solar system that ceased to exist billions of years before humans evolved. It survived the death of its home system. It drifted through interstellar space for epochs. It witnessed the formation and evolution of countless other stellar systems. It saw the Milky Way develop its spiral structure. It was already ancient when our sun ignited. And then, by chance, its path intersected with ours. For a few brief months in 2025, humanity got to study this ancient visitor. We measured its chemistry. We tracked its orbit. We watched it bleed ice and change colors and scatter light in ways we'd never seen. We asked questions about its nature. We wondered if it might be more than it appeared. We calculated what would be possible if it were artificial. We explored the darkest implications of the dark forest hypothesis. But mostly, we just watched in awe as this messenger from the ancient universe blazed through our neighborhood and disappeared. The ancient comet came. It dazzled us with its mysteries. And soon, it will vanish into the vast, dark forest of interstellar space, carrying secrets about cosmic noon back into the eternal night between the stars. We may never see anything like it again in our lifetimes. We may never get another chance to study matter from that era of galactic history. We may never know if our interpretations were correct, if our observations captured everything important, if we asked the right questions. 3i divided by Atlas is gone now, or almost gone. By the time you watch this, it might already be past Jupiter, accelerating toward the heliopause, preparing to leave our solar system's sphere of influence forever. And that, perhaps, is the most unsettling thought of all. Not that it was dangerous, not that it might have been artificial, not even that we're defenseless against future interstellar impactors. It's that the universe sent us a message from 13 billion years ago, a physical sample of matter from cosmic noon, a visitor from the thick disk carrying chemistry from dead stars and extinct planetary systems, and we only had a few months to study it before it disappeared forever into the darkness. What else is out there, traveling between the stars, carrying messages we'll never receive? What other ancient wanderers have passed through our solar system undetected, unseen, unknown? What secrets are written in their chemistry, their structures, their impossible behaviors? And when the next one arrives, because there will be a next one, eventually, will we be ready? Will we have better detection systems, better intercept capabilities, better protocols for studying objects that don't behave like anything we've seen before? Because here's something that keeps astronomers up at night. We only discovered 3i divided by Atlas because it got bright enough to see, because it started outgassing heavily, because it developed that distinctive coma and tail that made it stand out against the background stars. But what about the objects that don't do that? What about the dead comets, the ones that exhausted all their volatiles millions of years ago? What about rocky interstellar asteroids with no ice, no outgassing, nothing to make them light up as they pass through? Those objects would be nearly impossible to detect. They'd be dark, non-reflective, moving fast through the solar system with nothing to announce their presence. They could pass within the orbit of Mars and we'd never know they were there. In fact, they probably do, all the time. Statistical models suggest that for every interstellar comet we detect, there might be dozens or hundreds of interstellar asteroids passing through undetected. Maybe thousands. Our solar system isn't a closed environment. It's a highway. Objects are constantly coming and going, most of them invisible to us, traveling on hyperbolic trajectories that carry them through and out before we even realize they were here. And every single one of those objects is carrying information. Chemistry from other star systems. Isotopic ratios that tell stories about nucleosynthesis in different stellar environments. Structural information about how planetary formation works under different conditions. Every single one is a scientific treasure trove. A sample return mission from another stellar system delivered to us for free. And we're missing almost all of them. The detection rate for interstellar objects is improving. The Vera C. Rubin Observatory, when it comes fully online, will survey the entire visible sky every few nights with unprecedented sensitivity. It should dramatically increase the number of interstellar objects we detect. But even with better detection, we'll still face the same fundamental problem. By the time we detect these objects, they're usually already on their way out, already past their closest approach, already accelerating back toward interstellar space. We get to watch them leave. That's it. Actually intercepting one, sending a spacecraft to study it up close, collecting physical samples that requires detection much earlier in its approach, plus rapid mission development and launch, plus spacecraft capable of matching the enormous delta V requirements. It's technically possible. Conceptual studies have shown how it could be done, but it would require infrastructure we don't currently have. Pre-positioned interceptor spacecraft, launch systems on standby, autonomous probe swarms ready to deploy on short notice. It would require taking interstellar visitors seriously as scientific priorities and dedicating real resources to studying them. And that brings us to a question that maybe doesn't have a comfortable answer. Why don't we? Why aren't we prioritizing this? Why isn't there a major international effort to develop the capability to intercept and study interstellar objects? Part of it is cost, obviously. Space missions are expensive. Developing new spacecraft designs and launch systems requires billions of dollars and years of effort. Part of it is the unpredictability. We don't know when the next interstellar visitor will arrive, or what trajectory it will have, or whether it will be worth the effort to intercept. It's hard to justify massive infrastructure investments for events that might happen once every few years with no advance warning. But part of it, and this is the uncomfortable part, might be that we're not entirely sure we want to know what we'd find. Think about it. Every interstellar object we've studied closely has surprised us. Oumuamua had that weird, non-gravitational acceleration that still doesn't have a fully satisfactory explanation. 2I divided by Borisov looked like a normal comet but came from a stellar system with completely different formation conditions. And 3I divided by Atlas has all these bizarre properties we've been discussing. What if we actually intercepted one, flew a probe right up to it, collected samples, analyzed its surface composition in detail? What if we found something we really couldn't explain? Not just weird chemistry that requires new models, but something genuinely anomalous. Something that challenges our fundamental understanding of natural processes. What if we found evidence of processing, of refinement, of structures that can't form naturally? What if we found evidence that someone else has been visiting our solar system, studying it, leaving things here? What if the dark forest isn't just a hypothesis? Now, to be absolutely clear, there's no evidence that any of this is actually happening. The natural explanations for everything we've observed about interstellar objects remain perfectly adequate. Weird doesn't mean artificial. Unexpected doesn't mean designed. But the question lingers in the background of every paper about these objects, every conference presentation, every private conversation between researchers who've spent their careers studying how planetary systems form and evolve. What if? And maybe that uncertainty, that slight discomfort with where the investigation might lead, contributes to the lack of urgency around developing interception capabilities. It's easier to observe from a distance, to model and theorize and publish papers about chemistry and orbital mechanics, to treat interstellar visitors as interesting scientific curiosities rather than potential game changers. But 3I divided by Atlas forced the conversation. The Dark Forest paper, controversial as it was, opened a door that's hard to close. It made it acceptable to ask the question publicly, to explore the implications mathematically, to think seriously about what we'd look for if we actually wanted to distinguish between natural and artificial. And that might be the real lasting impact of this object. Not the specific measurements we took, not the particular mysteries it presented, but the fact that it made us confront our assumptions about what interstellar visitors could be. Because the universe is old, really old, 13.8 billion years old. Life arose on Earth about 3.5 billion years ago. Complex multicellular life only in the last billion years. Technological civilization only in the last few thousand years. Spacefaring civilization only in the last 60 years. But the universe had 10 billion years before Earth even formed. 10 billion years for other civilizations to arise, to develop technology, to spread through the galaxy, to build things, to send things. If technological civilizations are even remotely common on cosmic timescales, then the galaxy should be full of their artifacts. Old probes, dead spacecraft, debris from engineering projects. Things launched millions or billions of years ago that are still out there, still traveling, still functioning or not functioning, but still existing. And some of those things would occasionally pass through our solar system, just statistically, just by chance. The galaxy is large, but it's not infinite. Objects in interstellar space do eventually encounter other stellar systems. Given enough time, given enough civilizations, given enough objects sent out into the void, some of them will pass through here. Maybe they already have, many times. Maybe we're surrounded by ancient artifacts and we don't recognize them because we're looking for specific signatures, radio signals, obviously artificial structures, and missing everything else. Maybe some of those captured interstellar objects in strange orbits around our sun aren't just gravitationally captured natural bodies. Maybe some of them are old monitoring stations, derelict probes, things left here intentionally by previous visitors to watch and wait and occasionally report home. Maybe cosmic noon, that era when 3I divided by Atlas formed, when star formation was intense and the galaxy was young and active, was also when the first great wave of galactic colonization happened. When the first technological civilizations arose and spread and built megastructures and sent out their probes and terraformed worlds and did all the things science fiction imagines, and maybe the thick disk where 3I divided by Atlas comes from is full of their remains. Ruins, artifacts, things that survived the death of their home stars and kept traveling, kept orbiting, kept existing long after their creators were gone. 3I divided by Atlas could be a sample of that era. Not just a comet, not just ice and rock, but a time capsule from the period when the Milky Way was alive with activity we can barely imagine. Or could just be a comet, ice and rock, natural processes, random chemistry from a random stellar system that happened to send this particular chunk of material on a trajectory that happened to intersect with ours. Both possibilities are terrifying in their own way. If 3I divided by Atlas is just a comet, it means the universe is full of objects we don't understand, carrying chemistry we can't predict, arriving without warning at speeds we can't match. It means we're vulnerable to impacts we can't prevent and contamination we can't control. It means the cosmos is weirder and more dangerous than we thought. If 3I divided by Atlas is something else, something artificial or at least processed by artificial means, it means we're not alone. It means someone else is out there, or was out there, and they've been visiting our solar system. It means the dark forest might be real. It means every interstellar object could be a scout, a probe, a warning, a weapon. Either way, we're not safe. Either way, we're not prepared. Either way, we're at the mercy of whatever the universe decides to send our way. And 3I divided by Atlas showed us that we don't even see most of what's coming until it's already here. Now, here's something that doesn't get talked about enough: the psychological impact of all this on the scientific community. Astronomers are generally cautious people. They are trained to think in terms of null hypotheses and statistical significance and peer review. They don't make wild claims. They don't speculate publicly without solid evidence. But behind the scenes, in private conversations, in the emails and Slack channels and late-night discussions at conferences, there's a growing sense of unease. Because every interstellar object we've detected has been weird. Every single one. In different ways with different anomalies, but consistently outside the bounds of what simple models predict. Oumuamua with its acceleration. 2I divided by Borisov with its unusual activity patterns. 3I divided by Atlas with its chemical composition and polarization signature and color changes and everything else. 3 objects. 3 weird objects. Now, maybe that's just selection bias. Maybe we only detect the weird ones because they're bright enough or active enough or unusual enough to catch our attention. Maybe the universe is full of boring, normal interstellar objects passing through and we're only seeing the outliers. That's the reasonable interpretation. That's what most scientists will tell you publicly. But there's another possibility that's harder to dismiss the more data we collect. What if they're all weird? What if interstellar objects, as a category, are just fundamentally different from solar system objects in ways we haven't fully grasped yet? What if the process of spending millions or billions of years in the interstellar medium, exposed to cosmic rays and interstellar chemistry and galactic magnetic fields and radiation from nearby supernovae and everything else that happens in the space between stars, what if that process transforms these objects in ways we don't understand? What if there are chemical reactions that happen over million-year timescales in deep space? Slow polymerization of organic compounds, gradual restructuring of silicate minerals, changes to the isotopic composition from cosmic ray bombardment? What if objects that spend enough time in interstellar space become something else? Something that doesn't fit neatly into our categories of comet or asteroid, because those categories were developed studying objects that have spent their entire existence inside our solar system protective bubble. 3I divided by Atlas might not be weird. It might be normal for an interstellar object. We might be the weird ones, expecting interstellar visitors to behave like local objects when they've had completely different evolutionary histories. And if that's true, it means we need to completely rethink our approach to studying these things. We can't just apply solar system models and expect them to work. We need new frameworks, new theories, new ways of thinking about matter that has existed in conditions we've never directly observed. But there's a deeper question underneath all of this, a question that goes beyond chemistry and orbital mechanics and detection rates. Why now? Why are we suddenly detecting interstellar objects at all? Oumuamua was discovered in 2017, first confirmed interstellar object. Before that, despite decades of astronomical observations, we'd never definitively identified anything from outside our solar system. Then 2 I divided by Borisov in 2019, 3 I divided by Atlas in 2025. 3 objects in 8 years. Now, the obvious answer is that our detection capabilities have improved. Better telescopes, better survey systems, more sky coverage, more computational power to analyze the data. That's definitely part of it. We're seeing these objects now because we finally have the tools to see them. But there is an uncomfortable alternative explanation that some researchers have quietly considered. What if the rate is actually increasing? What if there are more interstellar objects passing through our solar system now than there were 50 years ago? Or 100 years ago? Or 1,000 years ago? What could cause that? Maybe our solar system is passing through a denser region of the galaxy. Space isn't uniformly empty. There are molecular clouds, stellar streams, regions where the density of interstellar matter is higher. If we're moving through one of those regions, we'd encounter more objects. Maybe something happened elsewhere in the galaxy that ejected a bunch of material all at once. A star went supernova. A close stellar encounter disrupted multiple planetary systems. A galactic merger event sent debris flying in all directions. And now, millions of years later, that debris is reaching our neighborhood. Or maybe, and this is pure speculation with no evidence whatsoever, maybe someone is sending them. Maybe after we began broadcasting radio signals in the 1,930 seconds, after the first nuclear detonations in the 1,940 seconds, after humans walked on the moon in the 1,960 seconds, and after the Voyager probes carried messages into space in the 1,970 seconds maybe, somewhere out there, someone noticed. Maybe a distant observer within a few hundred light years detected our faint signals and took note of a new technological civilization emerging. And maybe some of the interstellar objects we've seen like Oumuamua, 2 I divided by Borisov, or 3 I divided by Atlas, are reminders that the galaxy is older and more dynamic than we often imagine. Maybe they are simply natural visitors, fragments from other star systems that happen to cross paths with ours. Or maybe, just maybe, they are hints of something more, relics of exploration from distant worlds long ago. It's easy to assume coincidence, that better telescopes, more comprehensive sky surveys, and improved data analysis simply mean we're finding what was always there. And that's probably true, but still the timing feels curious. 3 I divided by Atlas arrived in 2025, a year when humanity is turning a new page in space exploration. Multiple missions to Mars are underway. International and private efforts are reshaping how we reach and study other worlds. Artificial intelligence is enabling real-time space observation and autonomous decision-making like never before. So, if someone were studying a young, developing civilization not with malice, but with curiosity, when would be the perfect time to look? Perhaps during the transition, when the species is just beginning to explore beyond its home planet, when it's advanced enough to detect the universe, but still learning its place within it. That's the poetic thought, at least. The scientific truth is far simpler. 3 I divided by Atlas appears to be a natural interstellar comet, an ancient traveler from the galaxy's early days. The evidence supports that. it's the explanation that fits. And yet, even as we accept that, the questions it raises remain. Questions about what it means to be a civilization capable of noticing visitors from other stars. Questions about how often such travelers pass through, unseen. Questions about how much of the galaxy's long history is still written in the silent motion of its debris. 3 I divided by Atlas came from the distant past, from a time when the Milky Way was young, when stars were forming rapidly, when the elements of life were just beginning to spread. It traveled through interstellar space for eons before arriving here, briefly crossing paths with a world capable of asking what it is and where it came from. And now it continues on its journey, back into the vast dark between the stars. Maybe its legacy isn't about answers at all. Maybe it's about the questions it leaves behind, questions about who we are, where we come from, and what other stories might be traveling unseen through the deep night of the galaxy. It will travel for millions more years, maybe billions. Maybe it will encounter other stellar systems. Maybe other civilizations will detect it and study it and ask the same questions we asked. Or maybe it will drift alone through the expanding universe until the last stars burn out and the cosmos goes cold and nothing remains but distant galaxies receding from each other faster than light can travel between them. Either way, 3I divided by Atlas is gone from our lives now. A brief intersection of trajectories. A moment of contact between an ancient wanderer and a young civilization just learning to read the messages written in starlight. We learned from it about cosmic noon, about thick disk chemistry, about how planetary formation works in different stellar environments, about the limitations of our detection systems and our theoretical models. But mostly we learned that we don't know. That the universe is bigger and stranger and more full of mysteries than we had quite appreciated. That visitors from elsewhere bring questions we're not prepared to answer. And that maybe, just maybe, we need to start taking those questions seriously. Not as idle speculation, not as science fiction scenarios, but as genuine scientific problems that require resources and attention and careful thought. Because 3I divided by Atlas won't be the last. There will be others. More interstellar visitors arriving without warning, carrying chemistry from dead stars, following trajectories that defy probability, behaving in ways that challenge our models. And each one will force us to ask the same questions again. Each one will make us wonder whether this is the one that's different, the one that's not natural, the one that proves we're not alone, or each one will be just another comet, just another chunk of ancient ice and rock, just another messenger from the deep past carrying information we barely know how to read. Either way, they're coming. They've always been coming. We're just starting to notice them now, and we need to figure out what we're going to do about it. Conclusion. So that's the story of 3I divided by Atlas. The ancient visitor from cosmic noon that bled water in the void, scattered light in impossible ways, changed colors from red to green, and disappeared behind the sun during its closest approach. It's not staying in our solar system. It's not an alien spacecraft. It's not going to impact Earth. But it revealed something important, something we needed to understand. We're not as isolated as we thought. The solar system isn't a closed environment. We're connected to the rest of the galaxy through a constant flow of visitors carrying messages from places and times we'll never see directly. And we're vulnerable to impacts we can't prevent, to contamination we can't control, to encounters we might not recognize until it's too late. 3I divided by Atlas gave us a warning. Not a threat, a warning. The cosmos is stranger than we imagined, and it's full of travelers. If you want more deep dives into cosmic mysteries that'll keep you up at night, subscribe and hit the bell.